All right, guys, welcome back to chapter 17. So, today we're going to be diving into a pretty good size of the Security Plus exam, all about the vulnerabilities and attacks. Now, we're going to break down different ways that systems themselves can be compromised, from the hardware itself to the software running it. Now, in order to pass the exam, these are going to be some of those fundamental understandings that everything we do in cybersecurity, from defense to the mitigation to red teaming to, well, everything. So let's take a quick look at the agenda for this session. We're going to start with the physical layer. We're going to talk about the hardware vulnerabilities. Once we're done there, we'll talk about some wireless protocols with Bluetooth and mobile attacks. We'll cover a high priority topic called zero-day vulnerabilities. Then we'll dig into what we like to call the operating system vulnerabilities, or the flaws. Now, we're going to spend a good time on application attacks. Specifically, we're going to be talking about SQL injection and XML injections, and learn the difference between cross-site scripting and cross-site request forgeries. And then lastly, we'll wrap up with some of the basics of buffer overflows and race conditions. Now, we've got a lot to cover on this, but by the end, you'll be ready for the exam itself. So, what is a hardware vulnerability? Well, the formal definition is any weakness or flaw in physical devices and their components. Now, any of these components can be exploited. So, think of this as a security hole that is baked into the silicon, into the actual circuit board itself, or the physical design of a device before the software is even loaded. Attackers can use these flaws to gain unauthorized access, manipulate operating systems and system operations, or even compromise the integrity of our data. Now, a famous example of this would be like the Spectre meltdown vulnerabilities found in modern CPUs. So let's discuss some of the items that are in this category themselves. Now, there are a few different slides, a few different vulnerabilities as we come through here. And one of them could be like your side channel attacks. So a side channel attack is where an attacker is actually taking the physical properties like power consumption or sound or even electromagnetic radiation to steal something from your machine. Okay, so they're listening in, but they're not directly connecting. They're utilizing something external to the system to actually get in. We have fault injection, where we physically can zap the device with electricity or a laser to cause an error or bypass of security checks. And then we also have the vulnerabilities in firmware, such as BIOS or UEFI, which can basically give an attacker access to the machine even on a system reboot. So how do we mitigate some of these hardware vulnerabilities? Now, this is going to be tricky because you can't always just patch a physical chip. So key mitigation strategies that might include would be, well, we might have firmware or microcode updates from the vendor. This is the most common method. If they can fix some of the vulnerabilities with software, they'll do it. We also can do implementing of secure boot and maybe trusted platform modules, or otherwise known as TPMs, to ensure that the hardware and the boot process can't be tampered with. And in severe cases, the only fix might be even hardware replacement. Now, of course, strong physical security by keeping unauthorized people away from the device is probably number one for these kind of physical vulnerabilities that we have within our systems. So next up, let's talk about a protocol that we all use every day. Let's talk about Bluetooth vulnerabilities and attacks. This is going to be a major part of the mobile and IoT security landscape for the Security Plus itself. Now, at the core, on a Bluetooth attacks take advantage of flaws in the Bluetooth protocol. They might take advantage of implementation errors or even user misconfigurations. Now, there could be a couple different ways that this happens. The protocol itself can have a flaw. The company who wrote the code on the device could be buggy. Or the user can simply misconfigure their settings by leaving their device discoverable all the time. Now, You want to be familiar with the specific types of vulnerabilities. Things like Blueborn, which was a collection of 0-day vulnerabilities that allowed an attacker to attach to a device. So there's a whole bunch of different vulnerabilities, and we're going to talk about a few of them. Now, for specific attacks, the first one that we want to know for the Security Plus is called bluejacking. This is a harmless but annoying Bluetooth attack where the attackers themselves send unsolicited messages or files by nearby Bluetooth enabled devices. As this diagram suggests, the attacker first scans for Bluetooth enabled devices. They don't really gain access to the machine. They often will try to send a contact information or unsolicited messages. Now, the key difference between bluejacking is that it's primarily just annoyance. It's spam, okay? They're not stealing your data, but for the exam, remember that jacking is like sending junk, okay? Bluejacking is just sending junk to your device. Now for the serious one, blue snarfing. Now this one's more serious of an attack because this is what's going to allow an attacker to gain unauthorized access to a device without the user's knowledge. Now notice the difference. Bluejacking is sending the data to the device. Blue snarfing, on the other hand, is stealing data from a device like your contacts, calendars, or even files off your device. So I like to say for the exam, remember snarfing equals stealing. So S and S, J and J. Remember, jacking is just a bunch of junk, a bunch of spam, while snarfing is about stealing information itself. Now, the third one that you need to know is going to be blue bugging. Blue bugging is one of the most severe out of the three. Blue bugging is an attack that allows an attacker to gain access to the victim's Bluetooth-enabled device. We're not just talking about sending messages or stealing files here. We're talking about total access and control of your device. As the slide says, the attacker themselves can access all the information such as photos, apps, contacts, everything. They can even call, send messages, and essentially use your phone as if it was in their hand. Now, this attack takes advantage of making sure that your phone is takes advantage when your phone is discoverable with Bluetooth. This is a harder form of hacking than bluejacking or blue snarfing. Now, as a prevention tip, there's no clear-cut way to make sure your phone is set to invisible mode or non-discoverable. It makes it harder, but always be cautious when you're using open Wi-Fi in busy or untrusted locations, like those coffee shops. All right, Bluetooth impersonation, or BTI, is what we like to say. In this attack, an attacker masquerades as a trusted device by mimicking its Bluetooth address and communication patterns. So if you look at this diagram, you have Alice and Bob, and we trust each other and share a key. The attacker, Charlie, impersonates Bob to trick Alice or impersonates Alice to trick Bob. This essentially is a man-in-the-middle attack. Okay? It's a man-in-the-middle attack for Bluetooth. The goal is to get one of the devices to connect to the attacker, thinking it's connected to a trusted device, which allows the attacker to intercept data. So how do we mitigate some of these Bluetooth attacks? Well, we've already mentioned a few, but let's summarize a couple. For one, disable Bluetooth when you're not actively using it. This is probably the most simple and most effective way to protect against your device or protect your device. We may want to set your device to not discoverable or invisible mode. It helps from being detected from other devices around you. Keep your device's firmware updated. Vendor release patches for these vulnerabilities all the time, so keep it patched. Do not accept pairing requests for devices that you do not recognize, and routinely go through your paired devices. Okay, list and unpair or forget devices you no longer use or trust. Now this is going to lead us into the next section. We're going to talk about mobile vulnerabilities. Now this does include Bluetooth, but it also has Wi-Fi, cellular, and application level weaknesses on our smartphones and our tablets. Okay, So when we're talking about mobile attacks, we're covering a wide range of threats that can be highly testable. Now, this could include a whole bunch of things like malicious apps or malware downloaded from untrusted or third party stores. It could be phishing or smishing, which is SMS phishing, to steal credentials. It could be Wi Fi sniffing, such as on public or unencrypted networks. It could be data leakage from apps that are overly permissive and access your contacts, locations, or microphones when they don't need to. Could be even jailbreaking for iOS or rooting on Android, which bypasses all the built in security functions, making it much more vulnerable. Now, this slide gives us an excellent checklist for mobile security, and these are all best practices we should know. Now we're going to see some repeats here. So first we need to keep our software updated. Patches for the OS and applications should be patched. We should use trusted app stores such and avoid side-loading apps. Okay, we need to use the iOS store and the Android Play Store. Don't be side-loading apps when you don't need to. Enable device encryption by default. So that way if the data or the phone is stolen or the mobile device is stolen, or lost, that the data itself is going to be secure. Use strong authentication, like a strong passcode or biometrics, or even combined with a PIN. Avoid using public Wi-Fi and sensitive for any sensitive transactions. If you do need to use it, maybe use a VPN. Disable Bluetooth and Wi-Fi when not in use. And then finally, how about we install a security software like a mobile antivirus or an anti-malware solution for our device. All right, this was going to be a big one here. We're going to talk about zero-day vulnerabilities. You're definitely going to see this concept on the exam. So this is going to refer to that previously unknown flaw or weakness in the software that is maybe discovered by attackers, but the vendor or developers are either not aware of it or have not developed a patch for it. Now, as the name suggests, the 0 day means developers had 0 days to create a patch. The moment this weakness becomes public, an attacker is already using it, and there's no official fix. Now, this is very, very dangerous. Remember, a 0 day exploit is the actual malicious code or technique to attack the 0 day vulnerability. A 0 day attack is the use of an exploit in the wild. Now, there are different types of 0 day attacks. While vulnerabilities are often just categorized by what they affect, like 0 day in a browser versus 0 day in an operating system, it's more useful to think of it as a life cycle of a 0 day attack. So it's always going to start with an unknown vulnerability. An attacker is going to discover it and write an exploit. The attacker will use the exploit in the wild. This is known as the 0 day attack. And eventually the vendor discovers the attack, develops a patch, and releases it. Once the patch is available, it is no longer considered a 0 day. It is just considered a known vulnerability. Now, 0 day attacks can come in all shapes and sizes, so just know that 0 day is all about whether or not the patch is available or not. Next, let's look at the operating system vulnerabilities. This is definitely another foundational section of cybersecurity because everyone's going to be using an operating system. And so an operating system is just any weakness within the OS vulnerability is a weakness within the operating system itself that can be exploited by attackers to gain unauthorized access, execute malicious code, disrupt services, or even steal information. Now, there are plenty of weaknesses or flaws within an operating system that can be exploited by attackers. Now, the goals are going to be varied. It could be maybe to gain unauthorized access, maybe execute malicious code, disrupt services, steal information. Essentially, these are going to be bugs in Windows, Mac OS, Linux, Android, or even iOS that will let an attacker do something they shouldn't be able to do. Now, the most common goal here is probably going to be privilege escalation. This is where a regular user can then become an administrator or a root user, even though they were not, technically supposed to be one. So there are a couple different ways of looking at this. So we can look at common vulnerabilities, right? That's on the previous slide. Improper privilege handling, which leads to privilege escalation. Maybe unpatched systems, missing patches, very common. User just hasn't patched their system in a while. Maybe default or weak configurations, or just insecure default services, like using Telnet or FTP. These are definitely something that's just, well, these are weaknesses in our system that we can either protect by doing multiple different things. And how do we mitigate some of these OS vulnerabilities? Well, should be a review for you at this point. First one would be patch management. We need to keep all the OS and applications updated. You're starting to see probably a trend here by now. Now we need to make sure our system is hardened, which is technically in the next chapter. This means turning off any unnecessary services, closing unused ports, and applying security controls based off of a security benchmark. Now, that benchmark might be a best practice from the operating system vendor themselves, or even provided by compliance or other regulatory bodies. We may want to use a host-based or host-based intrusion protection system. So we got firewalls or IDS, IPSs. We may want to install antivirus or anti-malware software. We do want to make sure that we have the principle of least privilege. That way that users and applications should only have the minimum permissions necessary to do their jobs. We don't want to have everyone be an administrator. All right, you see this word EDR at the bottom as well. Just make sure that we might have endpoint detection. Basically, all the software rolled into one that helps us keep an eye on our fleet. Now, we're moving up to the application layer itself. Let's talk about two of the most famous and dangerous type of injection attacks. Let's talk about SQL and XML injections. Now, these two types of attacks can exploit vulnerabilities within the applications. They can help manipulate database queries and look at things like XML data structures. Now, in both cases, whether or not you're talking about SQL or XML injections, just know that it's improper input validation. The application takes user supplied data, like from a search box or a login form, and just trusts it by putting the command directly into the data structure itself. Now, a SQL injection attacks the backend database, while an XML injection normally attacks the XML parser, which is often used for configuration files or transmitting data between applications. So let's look at this classic SQL injection example. A legitimate user would enter their username like John and their password like password123. Now the query is going to become where username equals John and password equals password123. Now this is going to work as expected, but an attacker doesn't enter a real name. They might enter other types of strings like single quote or 1 equals 1. Okay? Or they'll say single quote or 1 equals 1 dash dash. Now, what happens behind the scenes is a database is going to evaluate this. Username is going to be username equals quote quote. It's just going to be empty. But then it's going to look at or 1 equals 1. So if we think about our scripting software, we'll think 1 equal 1. Is that true or false? That's true. So since this is true, then it will go to the where clause. Now the where clause is true on every single row of the database, so it may return all rows from the user table and effectively logging into the attacker into either the first user in there, which a lot of times is admin or root, without even a valid password. Okay. Now this is classic authentication bypass techniques. Now XML, on the other hand, might use a different type of code itself. Now we may have a user block with a username and a password, but the attacker might inject an extra field called role. Now they're going to send the same username and password, but in the role, now they're going to say, hey, I'm an admin role. Now, if the application is poorly written and doesn't validate the input from the schema, it might parse this entire structure when it was created the user session and also inject the role tag, giving the user admin privileges. So how do we mitigate these type of attacks? Well, this is a critical question for the exam. The number one defense for SQL injection or XML injection is going to be input validation. This means that we need to check all user input to make sure it matches the expected format. Is this a valid email? Is this number in the right range? Does it contain some weird characters that I normally don't see in a username? So the best defense for SQL injection would be parameterized queries, also known as prepared statements. This separates the SQL command from user supplied data. Now the data is treated only as data and never executed as a command. Now this makes injection impossible. Now for XML, we might need to use something that we call a secure XML parser. This is configured to disallow any dangerous features, like validate the XML to a defined schema or layout, so that way we know that they're not just injecting extra data within our data stream. So know the two different type of injections. 9 times out of 10, we're talking about input validation to fix it. Now the next two type of attacks are going to sound similar, but they're very, very different. And so I do want to talk about them separately. Let's talk about cross-site scripting and cross-site request forgeries. So let's break them down. Now, the first is going to be the cross-site scripting, or XSS. Okay. Now, this type of attack is when an attacker injects malicious scripts into a web page that are viewed by other users. The malicious script, usually JavaScript, is normally going to run in the victim's browser. Now, it's going to be on a trusted website, but this could be used to steal cookies, capture keystrokes, or even redirect users to fake websites. The key to cross-site scripting is this. It exploits the trust of the user has for a certain website. For instance, maybe you trust Facebook.com. Well, if I put a script within a comment, when you view that comment on your computer, does the website allow scripts to run on the user's computer? If so, that's a cross-site request forgery, or cross-site script. My bad. Now let's talk about request forgeries. So the second one here, the request forgery. Now the attack tricks a victim into performing an unwanted action on a web page. Okay. The attack doesn't inject a script on a site, it forges a request. It tricks your web browser, which is already logged into your bank, into sending hidden request information to that bank, like transfer money to this other account. Cross-site request forgery exploits the trust of a website from a user browser, so it's almost backwards. Okay? So let's look at this basic cross-site XSS example, cross-script. An attacker enters the following code into a website, which is script alert XSS attack script. If the website does not sanitize this input, the malicious script is stored in the website's database. When another user visits this website, the script is going to be executed in the browser, displaying an alert message. Now, an alert box is harmless, but an attacker could just as easily write a script to steal document.cookie and send it to their own web server. This specific example is a stored cross-site script or a persistent XSS, because the malicious script is permanently stored on the web server. Now, for the Security Plus exam, you need to know there's 3 types. There's stored, reflected, and DOM. Stored is what we just saw. It's a malicious script that's stored on the target system, like through a database or a comment field or a forum post, and stored, loaded on any time a user visits that page. Reflected is not stored. It's reflected off the web server. It's usually done with a malicious link. An attacker sends you a link, you click on it, the link includes the script as part of the URL, and the website takes the script from the URL and puts it onto the page, and your browser runs it. And then lastly, we have DOM based. This is the more modern type of cross site scripting, where the entire attack happens in the client side code, all in JavaScript, all inside your victim's browser. The server normally isn't involved at all. Okay? Now, the impact here for cross site scripting is very significant. An attacker who successfully executes a cross site script can steal cookies or impersonate you. They can perform key logging or capture credentials from fake login forms. They can scrape any information that is visible on the page. They can perform phishing or redirect you to a malicious site. So we have to be careful with this with our end users. Again, input validation is going to be key for cross-site scripting. But more specific, we need to do output encoding. Output encoding means that whatever you display, a user-supplied data on a page, you must encode special characters. For example, if we do an open character, it will become the special character as ampersand LT semicolon. Okay. When the browser sees it, it will only display the literal text on the page but not execute the script itself. Basically, we're going to neutralize any attack that they attempt to do. Now let's look a little bit closer at cross-site request forgery. And we're going to go through like an example here. Step 1, the user logs into a web application such as an online banking site, and their browser stores the session into a cookie. Okay? This means that the user is now authenticated. The attacker tricks the user into visiting a malicious website. That could be done through a phishing email or a link in a forum, and the malicious site will have some hidden code on it. For example, in the HTML post, it might be like bank.example.com/transfer. The attacker account and the amount will be as hidden inputs, and a bit of JavaScript that will submit it will automatically load the user page. The malicious request will be sent to your banking site, and because you are already pre-logged into the site, the browser will helpfully attach the session cookie to the request, and, well, guess what? The bank thinks you're legitimate and just runs the transfer of the funds. Now, the impact of this, well, you can see it as being, well, any state-changing action without consent. This is going to happen behind the scenes, and it's pretty hard to know that it happened. So this could be like transferring money, changing their password, deleting data, or even making a purchase. So if you ever leave any websites logged in, just know that this cross-site request forgery is always an attack that an attacker can complete. Since the attacker can't see the response from the bank itself, they can cause the action to happen. They're just going to be able to see this as a, well, did someone fall for it? If so, I've got money in my account. Okay. Now, how do we mitigate cross-site request forgery? Well, there's a couple ways that we do it legitimately. We're going to use anti-CSRF tokens, which, by the way, any program that uses authentication should be using this by default now. Now, here's how it works. When the user loads in a legitimate form, like a transfer funds page, the server is going to generate a unique secret random token and embed it in the form. When the user submits the form, the token is sent back. The server will check the token to make sure that it matches what it sent, and if for some reason it doesn't match what it sent, then we know that it's a fake attack. And so normally what happens is the attacker will send it in, but it won't be able to know what the token is, so it will either make one up or not have one on there, and the server will reject the request. A modern defense here would be like the same site attribute on cookies. There's a couple other ways of doing this, but just know that basically we can look at a few different things to make sure that, hey, when you logged in, is it still the same session, or is something funky going on here? All right, let's talk about one of the oldest and most powerful attacks in the book, which is called a buffer overflow attack. Now, a buffer overflow attack happens whenever a program writes more data than the buffer can hold. A buffer is just a fixed size of memory, so think of it like filling up a cup of water. and you try to put too much water into it, it's going to overflow. So let's look at this C example real quick. This where a programmer defines a buffer that holds 10 characters. The next line uses string copy to, well, say this is a very long string into our buffer. The string is much larger than 10 characters. The extra data doesn't just disappear, it might just get written into the adjacent memory, overflowing the buffer. This overflow can either corrupt data, crash a program, causing like denial of service attacks, or in a malicious attack can override critical program instructions to reflect the program and execute the attacker's own code within a higher elevated stack. Okay. Now there's two types of buffers that you should know about. There's going to be the stack-based overflow. This is the most common. Basically, the attacker overflows a buffer located in a program's stack, and the goal is just to overwrite the return address to hijack the program's execution. So basically, just change the way that it runs and, well, either change it or crash it. The second one is a little more complex. It's called a heap-based buffer overflow. It involves overflowing a buffer in the heap, which is another memory area for dynamic memory, to corrupt program data in a way that it eventually leads to code execution. Now, for Security Plus here, the key concept here is you're writing too much data into a fixed space that's going to have unintended malicious effects. Okay. Now, how do we mitigate buffer overflows? Well, there's a whole bunch of different ways of doing it, but from a developer's perspective, we should definitely make sure that we are doing secure coding practices. We need to avoid dangerous functions like string copy and use safe functions instead, like string end copy, which will let us specify the maximum number of bytes to copy. We might want to do input validation. We might do address space layout randomization or data execution prevention, DEP. Basically saying there are just different ways to protect this, but 9 times out of 10, it's going to come back to the coding practice. So how do we prevent buffer overflows? We need to protect it from the beginning when the program itself is generated and protected. Now you'll notice a lot of patches out there that are going to be like, this fixes a buffer overflow in process X. And that's what we see a lot. Now our final topic for this slide deck is going to be race conditions. This is a more subtle type of vulnerability. Now a race condition occurs whenever a timing of a sequence within our system happens perfectly. It's a classic vulnerability that is when multiple processes or thread are running on a computer, do they have access to the same resources simultaneously? Now, one of the biggest names here is TOC-TOU, time of check to time of use, okay? Now, a time of check to time of use is a race condition. For instance, the program might check for, well, safe.txt. Is it owned by the user? The answer might be yes. Before the program uses the file, time of use, the attacker changes the file. They delete safe.txt and replace a symbolic link to etc password wd. The program then uses the file, opens what it thinks is safe.txt and writes to it, but it's actually writing to the system's password file. Major privilege escalation. So here's another example from like a banking industry. Let's say you have $100 in your account. Thread A reads the balance, which is $100, and adds $50 to thread A's internal value. So now you should have $150. But before thread A writes the updated balance to 150 back to memory, thread B reads the original balance as 100 and subtracts $30. Now thread B internal value is $70. Thread B writes the updated balance of $70 back to memory. Now the official balance is $70. But thread A hasn't completed yet, so they're going to then update it back to $150, overriding the changes made by thread B. The final balance is $150. Although it should have been $120 because, well, the $50 was added, but also $30 was spent. Now the $30 deduction is completely lost. And this is a critical data integrity failure, okay? We need to make sure that if we do if we're making changes to the same location, then we have things that are locks. And so this is a typical time of check to time of use vulnerability. Okay, that's the one that we just went through for the banking type itself. Now the key takeaway here is anytime you use a shared resource like a file, memory, or multiple processes, you have the potential for a race condition. If you don't manage the access properly, you'll have issues. This is why we use like file locks or thread locks when we're dealing with databases. Definitely make sure that we take care of things. All right, guys, that brings us to the end of the lecture material. We've covered a huge amount of stuff here, so you may want to watch this video again or read the chapter again. From hardware attacks to complex application layer vulnerabilities, let's make sure that we understand this. This one's very term heavy, so make sure you go through your terms and just know what each one of these are. If you could describe to me what each attack is and maybe a possible mitigation step for it, you're now on your way to pass the Security Plus. So good luck on this, and I'll see you for Chapter 18.